1, 2. Hallo, hallo, geht das? Ja. Okay, I guess we're going to start with the typical language poll. How many people in this room need to hear that in English? Raise your hand. Okay, fine. Sorry for the Germans. Have to do it in English. Okay, let's officially start it. This is the almost annual Finley talk, and this time we're trying to, well, get out of the Cisco land into Windows land, and basically tell you our experiences, what happened, and yeah, how to solve certain problems that might arise. So, the agenda. We're looking at vulnerabilities, especially in the white char environment, most commonly referred to as Unicode overflows. Look at the problems there for stack-based buffer overflows and for format strings. Then we look deeper into the problem of finding a return address for Unicode overflows, and we'll discuss different ways to do that. And well, I'm gonna be bold and try to tell you that I finally solved the return address problem on Windows. You're free to flame me at any time. And then we're discussing shellcodes for Unicode, the normal shellcode that is, for some of you, probably known as Venetian shellcode, and some simple versions of that don't really need any big, magic. And of course, a little bit annual Finolate Ode, so that you are rewarded for sitting here and listening to me. So after that, you can go out and go to the website and download stuff. And I figured I put it up before the speech, and guess what? It's up, and guess what? It doesn't work because the provider, well-known provider in Germany called 1&1, has this cool feature that the web server assumes if it's called .pl, then it will be a CGI. Well, it's not, and so you can't download them, and I have to fix that after a speech. Okay, talking about normal overflows. The typical classical hacking 101, please overflow my application thingy. We got a buffer, we got a saved frame pointer, saved return address, and the arguments to the calling function. What happens if some very talented C coder does a string copy or sprintf or, well, all the things that IDA is so happy to find for you? What happens, of course, is it overflows all the stuff. Then the function wants to return, so it restores the frame pointer. Frame pointer gets a funny number. Then the instruction pointer gets a funny number. And, well, look what happened. So, now we're moving to Windows land, and especially with Windows being native Unicode, we got the problem that a lot of the applications that we're so happy to feed a lot of ACE to tend to convert them into white char. So what happens here is we put a bunch of ACE in there, and it does a conversion, so it ends up being 0A, 0A all the time. And of course, those end up in the registers, and we have this problem that we're actually now influencing 2 out of 4 bytes in the return address, and not all 4 of them, which dramatically changes the whole picture. So let's compare them. In a normal overflow, we replace the frame pointer and the return address with user data. The same happens in Unicode overflows. Problem being that in the normal case, there's only that much of modification of the user data before it ends up in a register that it's not supposed to have it in the first place. So that really depends on the application. If you have a overflow that happens before any type of any type of sanitizing of user data, or in very, very well-written applications that don't do any sanitizing or input validation on user data, nothing happens. You have the full choice of what to put into the register. Here, you can guarantee that at least 50% of your data is screwed. Now, this problem is really basically a key space problem. I guess it's on the next slide. No. It's really a key space problem because your possible key space for return addresses is reduced dramatically. Now, what's the whole Unicode thingy? Most people actually claim that a Unicode translation just takes the input and places like a 0 byte next to every character, like this. So you got A, which is hex 41, and you got 0A. Well, this is not true. In Windows, pretty much all conversations I've seen are done with this function, multi-byte to white char. And the very important part here is the first parameter being the code page. Now, Windows actually ships with a lot of code pages pre-installed, but this gets very interesting, especially if you do HTTP-based exploitation or anything that might try to automatically determine your language. Why? Because your key space for return addresses, the way the translation is done, might actually change with the language that you supply. Now, let's take, for example, a HTTP overflow where you have the language field, client language acceptance field. If you set that to like being Japanese, the Unicode page that is used for translation might be different, or actually will be different in many cases, to, let's say, if you said English. Now let's look at those transformation tables. Those are the standard pages that are installed in Windows and used. There are actually more. There is a, what's that, special character page and a Macintosh conversion page, actually. Those two I've seen on English and German Windows 2000 systems actually don't translate. You get pure 0 bytes. The most commonly used is Ansi. It's the one here. But OEM is often used, and of course UTF-8 for pure Unicode implementation. Now here we have the Ascii character that's coming in, and here we have what came out of it in little endian order. So that's like the first byte, and that's the second. So far, it's fairly boring. It's really what most people say. It's like the character, like OC here, and then it's OC00. Nothing interesting. This goes on, actually, for most of the characters. You see, that's your standard Ascii character set. It didn't change. It's all zeros. Goes on and on. Most boring slides I ever made. But now, when the most significant bit of your character is set, it becomes interesting. Look at the Ansi translation. Here it is 80, but it becomes AC20. This is very, very important and very good for us. First of all, as I said, Ansi is the most commonly used page for the translations. Second, what we see now is that we can actually influence the second character. And for those of you who know hex a little, this is a space character. So in contrast to what you have with, let's say, in capital A, that you have a 0 byte right there, and a 0 byte being termination for a string in C is really bad for exploitation. Now you have a space character. Space character, well, shows you the same amount of information on the screen, blank, but doesn't terminate your string. Now you can actually play with that fairly effectively. But let's go on and look at the other translations here. You see there are lots of different translations, the second byte always being either 21, 02, 01, or 20. But then look at the OEM page. This is 90, this is C9, this is 91, this is E6. So you have to look at what translation is really done on your target system before you write an exploit or try even to find a vulnerability. Because as you see with the Unicode translation for Ansi, if you fuzz an application and put lots of capital A's in there, and it gets translated into Unicode, you get lots of 0 bytes. Well, if you put lots of 80 hex in there, you get a lot of AC20, which makes real strings and might actually find overflows that you don't find with capital A's. Besides, there is an increasing number of implementations out there that actually match user input to a number of 10 capital A's to prevent fuzzing. That's not a joke. Yeah, here you see more of the OEM translations that are actually different than the character here. You also see, for everything that has the most significant bit set, that the UTF-7 translation, of course, gets the FF character. I'm not going to go into details why that is. If you're really bored and you need some sleep, read the Unicode standards. And here, OEM becomes interesting. OEM becomes interesting because, again, we can influence 2 bytes of not being 0, and we get percent characters that might turn out to be useful for format strings. Yeah, more percent characters. You see, after the initial weirdness in the Ansi page, Ansi returns to be perfectly normal, which is probably the case why most people think that it's just the character and a 0 byte. Yeah. Let's keep boring. Okay, here it is. As I said, it really comes down to an address space problem or key space problem. You want to return from a function with the return address you supplied, which is basically why we are all here. The problem is that you had 4 billion choices, and now you have 65,535 average. So the problem is, if you look at the address space of an average Windows application, about 86% of this address space that you could possibly return to is not mapped. So unless you want to produce the biggest collection of Dr. Watson windows that you have ever seen, this is not useful. Also, Windows is heavily threaded, at least the applications are. And threaded applications tend to end up in memory areas that you don't know, and they keep changing. So even if you had one magic return address that ends up in your buffer, which is the classic way to do it, it wouldn't be really useful because you will have to do some magic like Hover presented, I think it was last year, or no, the year before, with making lots of threads and then killing them and then hoping to be the first thread. That's, well, not really reliable. And currently the most common method is actually something comparable to that. The most commonly used method right now is what's called blowing up the heap by supplying lots of data. Actually, for, let's say, for a remote overflow, you send lots of parallel requests in the attempt, actually, to get more memory mapped. The more memory is mapped, the more possible return places you have. And this is what KF of Snowsoft actually does quite a lot with, actually, in his case, local exploits. He's feeding them just lots of bullshit via environment variables, and just hopes that his buffer ends up in a place that is Unicode addressable. That is a way to do it, but as you can imagine, for remote exploits, you don't want to do that. So what about format strings? Well, format string vulnerabilities are almost extinct in the open source environment. They are very often found in a closed source environment because, well, it's hidden, so you can program whatever you want. Nobody's ever gonna find it. The thing being, format string bugs actually also happen in whitechar functions. Windows provides functions like fwprintf that take a whitechar argument as the first argument for the format string, or the second in this case, so that your string gets converted to whitechar, but is used as whitechar and is expected to be whitechar, so it's the same thing. Of course, the problem, again, is addressing, because also for format strings, if you want to write something, you have to provide an address. And, well, this is often also Unicode, so you're back to the same problem. For the Ascii versions, it's different, because you might end up having a string supplied to an application that is converted to whitechar, and then used in an Ascii function as format string. Now, you might ask, why should that happen? Well, we're hacking, so you might actually change the way this application works in an unexpected way. So it might actually happen, and of course, it wasn't planned this way. So the possibility is there, and the possibility is also there to use that. Problem here being that the format arguments are always 2 bytes. Now, if you have like %s or %x, those are 2 bytes. And if it gets converted into whitechar, you have a 0 byte in between. So that's pretty bad. You can, of course, do 3 character arguments, but the middle byte, as I said, becomes a 0, and that means and a string. And here is where the OEM pages with all the characters and the % signs come in handy. Of course, with those, you can at least do format string memory reading, because the addressing problem, as I said, is still there. And I doubt that there is a very practical way. There might be an exception, like in 1 or 2 applications, but in general, I doubt that it is very practical to use format strings with the address being unicoded. That's, well, pretty weird. But then again, hackers tend to do weird things. But anyway, you can still remotely read memory, so that's fairly practical. Yeah, here we got it in full color, because of, I'm bad in explaining stuff that I don't really understand myself. So this is the user input. You have like 4 capital A's, an underscore, and the format parameter. That's whitechar by Ansi, so you got like the 0 bytes in between. For a normal printf call, the first 0 byte would actually terminate the string, nothing happens. For the whitechar version, it actually works. So look for the whitechar versions if you got whitechar arguments, and you might actually find format strings. You will. Okay, return address selection. That's like where I spend most of the time thinking about, because that's really weird. You have this little key space of possible return addresses, and you need to, well, get something done to execute your code. Blowing up the heap doesn't actually always work. Why? Well, there might be, the application might actually not take more data than a specific amount. So what are you going to do? You can't blow up the heap because it's just not eating your stuff. It's unreliable because it's remotely totally unpredictable. You don't really know what happens. You can make it guesswork, you can make it advanced guesswork, but it will stay guesswork. And on the other side, while trying to use that method for exploits, I blew up a lot of other stuff with it, especially if you have an application that has more than one vulnerability. You might end up blowing up the heap and actually having overflows left and right while trying to exploit the one in the middle. So what you need is a jump or call to a register. Now, the registers have this nice little feature of often having a pointer to data that they're currently handling, because that's what registers are for. And of course, a function handling user input and mishandling it, which produces a buffer overflow, will have to have a register pointing to some user data. because it's currently handling this data. So that is the way to go. Now, the question is, you need code already existing in the memory space of the application to do that, and it has to be addressable with a Unicode string. That's fairly tricky, but if you find one, it's much more reliable and it will actually always work. So, how to find one? No, actually, there's another point. Of course, sometimes the registers don't point to user data. Like, one of the exploits I wrote had this problem that like every register contained either 0 or 1, and well, then the return address contained whatever I supplied. But this is not really useful because even if you have code that you can address and it jumps to register, well, there is still no pointer to user code, or to user data, so you can't execute code. But this nice little feature of a structured exception handling procedure in Windows can be used for that. Windows has this structured exception handler thing where every application can install its own exception handler. My guess is to prevent Dr. Watsons from showing up when you fucked up. So instead of like having a Dr. Watson tell you that Word crashed, it will just silently crash, which is, well, the Microsoft way of doing things. Now this ends up being on the stack. This structured exception handler actually is placed on the stack in most cases, or almost in all cases, I think. And so if you overflow further, not just the return address, but actually hit the first structured exception handler, then you have the pointer to the next SEH record here, and then you have the address of the SEH, of the structured exception handler itself. Now, if you supply this one, it gets fairly practical because the Windows handler code, the SEH handler code that's in NTDLL, will actually take places on the stack and put them into the registers, so the structured exception handler can actually find out what data was on the stack. So you are guaranteed to have a pointer, in this case for Windows 2000 it's EBX, a pointer pointing exactly here. It's pointing 4 bytes before the SEH handler address. So you know what register is going to contain which data, and you actually get code execution via the structured exception handler. Now you might ask how to produce an exception. Well, of course, if you overflow that much stuff, the exception is to be expected. Okay, in color. It's a weird thing, so I do lots of animations here. Basically what we do is overflow up to the SEH address, trigger the exception, which is like automatically done, and get code executed via NTDLL. So, you have seen, wait a sec. Buffer, frame pointer, return address, arguments, lots of other stuff. We don't really care. Here's the pointer to the previous SEH in a chain, and here's the SEH address. We just overflow it all, being as brutal as possible. Then NTDLL comes up. Well, decides it needs to call the handler, and is actually gonna do that. So, so we have a guaranteed way of executing our code. Now, back to the problem of finding this little 2-byte sequence that says jump EBX or call EBX. As I said, little key space, lots of code to cover. I tried to do that by hand, and I got so bored and pissed that I actually did something I shouldn't do. I wrote software. So the solution being pure, simple brute force. You can actually take a debugger, my choice being Ollie debug, and look at your program. You can attach to your target program and look at all the mapped memory. Now, what if you have a way of finding all possible return addresses by just doing all the conversions that are possibly being done, look if there is memory mapped, and if there is memory mapped, look at the code there. Now you would always find different sections of code that are mapped and addressable, but they will most definitely not contain a call EBX or jump EBX. Now what I do here is search from those locations down, because I don't care if in between of the addressable position and the actual call EBX, he pushes and pops and like moves stuff into EAX and moves stuff out of EBX and whatnot. I don't really care. The only thing I care about is the code between those two positions shouldn't touch memory. Why? Because it would most definitely produce another access violation and hereby ruin the whole exploit thing. So you can search from the point that you can address down until either it grabs memory, then yeah, you bail because that's not what you want, or it actually jumps or calls to some register. Now you might actually encounter jumps and calls in between to fixed addresses, which is where recursion comes into, because you can actually do the same thing from this address on. That's all pretty weird, so I actually did more because of the weirdness. Because when that worked, and I was fairly surprised that it worked, I realized that you can actually handle lots of other stuff with the same brute force procedure as well. And so I tried to put an end at those return address problems, because also you have still lots of Ascii-based overflows where you need a jump call register. And of course, for every overflow, you always have characters you cannot supply. Most often that's the 0 byte, but that also includes for HTTP-based overflows, character return line feeds, question marks, whatnot. Wouldn't it be really useful if you could just supply that all to your debugger and tell him, okay, now please scan the whole memory for jump call register addresses and, well, just remember them all. And of course, there are people doing more weird stuff, like Halvard told me he prefers a different method of getting code executed that is looking at the stack and find a pointer to a user buffer further up the stack, calculate the difference between the return he just did and this pointer to the buffer, and then find a piece of code that says add ESP whatever this difference is, return. Now, of course, we can support that as well. And thing being, if you got all those possible return addresses in your memory sitting in a plain list, why not save them to a file, walk over to a different Windows machine with, let's say, a different language and a different service pack, do the same thing here, and then just diff the addresses. Does anyone know what you get? Universal return addresses. So you actually get good return addresses, and the nice thing being, you have to do that once. Like, you spend an afternoon with lots of VMware images, and that's it. You got your universal return addresses for all possible combinations of Windows with like Korean language setting. Yeah, that all compiled together. There is a plugin called OliUni, because it was initially thought for Unicode. That's a plugin for OliDebug, and well, as of now, you can actually download it. This is how it looks, and this is what it finds. That's one thing that I'm actually using in an exploit. It's fairly interesting, because that shows this find a addressable position and then look from there. Now here, this position is addressable with the Ansi code page, because if you supply 429C, it gets translated to 00420153. And, well, but there is a push EDE, so it wouldn't really be useful. But here it just takes something from the stack, which you can safely assume to be not something that triggers an exception. it pushes a fixed number and it pushes a register, which we really don't care, but it then calls EBX. And as I said, EBX is going to contain pointer to the stack. You see here the stack pointer, and you see EBX, and those two are very close together. And so you can actually jump here, but end up calling EBX, which I thought is cool. Now, okay, we got a return address, and we got this, what I think, really brilliant brute force way of finding return addresses. Nice, nice. But, well, you put a shellcode in your buffer, it gets unicoded, and you are toast. Why? Because if you take, like, this piece of code here, and it gets unicoded, it becomes all kinds of crap that you don't really want. So, there are different solutions. The injected, most commonly OXO character, have to be planned for. So you create a, let's say, bind code that will, with all the zeros in between, actually bind a shell. That is considered fairly hard and not very practical. The other way would be code that uses something like padding to get rid of the 0 bytes. Actually code that will modify itself, and while doing so uses commands in between. No fear, I have a more clear slide than my explanation here. Let's take the freaking slide. Yeah. Okay, that is the different solution here. That's what you can use a one-character command like push EAX, and then have the 0 byte that ends up being here and here being in the middle, having a 6D. You actually just supplied the 50, the 6D, and the C3. And in Unicode conversation, you got like the 0 characters for free. And as it is often with like giveaways for free, they're really useless and just annoying. So this is why you put the 6D here, because it will basically catch those two 0 bytes here and here and make them a command that doesn't really destroy anything. You still execute code you don't want to execute, but as long as it is safe to do so, you still can use single byte commands, which is the easiest way to do a Unicode overflow. If you have data, let's say you have a register and it points somewhere in memory, and about like 10 different 10 characters after that, or 10 bytes after that, there is a user buffer that you can influence. You can use inc and increment and decrement EAX, because they're single byte commands. Put those in between, the 6D thing in between to catch the 0 bytes, and then like adjust the register a little bit, then push the register and return, which is easy, but most often the registers don't point to such convenient places. So Chris Enley from Next Generation Software, David Litchfield's little club, first published a paper called Creating Arbitrary Shellcode in Unicode Expanded Strings. He himself dubbed those, this technique, dubbed it Venetian shellcode, for the reason that it works like a Venetian blind. So the only known public implementation of that, because, well, okay, creating this by hand is painful. I tried, I failed, and like was about to eat my mouse. So you need something that generates this code for you. And well, Dave Vitale published a tool called makeunicode2.py, because everyone thinks that Python is way cooler than Perl those days. And so published it. Problem here is, it is initially part of a commercial software called Canvas that he sells. And so the procedure of separating this tool from Canvas was, let's say, done in a hurry. And it needs a lot of fixing. Actually, it doesn't really work correctly. But the technique works. And sometimes you can actually get good Venetian shellcode out of Dave's code. So what happens is you have your Venetian shellcode here, and then you have some, let's call it real shellcode below that, that you want to be without 0 characters. You want to be the way it was before the modification. So what you do is you address those bytes here that became 0 and change them using instructions that you can safely transmit for Unicode. So this is what it does. It like points to this place and translates it or modifies it. Same here for procedure. And then it actually, as you see, it's one memory block. So it will actually go on with the execution top to bottom. And when it hits this place here, it will actually execute normal code as you would supply in shellcode. So using the opcodes that do the padding, like the 6D we saw before, is okay. And well, you also need instructions to address the bytes you're modifying. So what Chris is doing, he's using add byte PTR EAX value, because that is 80 hex, 00 hex, and then the value. I hope you see the idea behind it. This 0 byte is not supplied to the process in the first place. When the string gets translated, it ends up being here, and so you look for instructions that actually contain at least 1 0 byte by nature, and so you can use the other half of the bytes you can influence to execute useful code. So he's using the add byte PTR, he's using add byte PTR EBP CH, what we have seen before, to do the realignment and get rid of 0 bytes that he's not looking for. And he uses exchange EAX ESP for getting the pointer to the code you're supposed to modify into EAX. That's a little bit problematic because of if you have a filter before that applied to your string that matches, let's say, for high bits, like the most significant bits, it's a problem because that's like 9/4 hex, and so the most significant bit is set, and that's, oh, well. Size is a problem, of course. Well, it's always a problem with overflows, but you have seen that you have to trick around quite a lot to get this stuff in memory the way you want it. Let's see here. You increment EAX, you do a little padding to get rid of the 0 bytes. You increment it again because, well, you had 1 byte for free that you already supplied, so you have to step over that. And then you do a little more padding, then you do the add byte PTR, whatever number you want it to be there. And then because the next instruction will be, and the next thing again will be a 0, which is missing here. Shit. Okay, imagine there's a 0 before the 60. You need another padding. So that is like almost 14 bytes to write 1 single byte. And that would be the code you supply, to the process before it gets converted. But 14 bytes is a lot for 1 single byte. You can imagine if you have an average shellcode size of, let's say, what's cool? Tezel, what's a good shellcode for Windows? 200, 300 bytes? Yeah, that would mean a lot of code to get this done. So, you have to look for something that is as small as possible to be created with your Venetian code. You don't want to create the full port binding, blah, blah stuff that goes like with exception handling and dynamic finding of load library A and whatnot. But you need to place something smaller, more effective in there, which Dave Eitel came up with, is a second stage shellcode. You have this Venetian thingy that just cleans up the mess that Unicode Translation produced in the first place. And then you have the second stage shellcode, go ahead and find the real shellcode, which is the third stage, basically. So, yeah, in numbers, the Venetian code creates the second stage code. Second stage code, like, searches the stack in ITIL's case for the real third stage shellcode, and then executes it, and, well, finally you get remote root. Now, while looking at those exploits and debugging them and, like, really not liking them, I realized there are also instructions with 0 bytes in there that can be used to make those Venetian shellcodes smaller. Why? Because there are instructions that have by nature the second byte being 0. If the second byte is 0 and your instruction is 2 bytes long, you don't need realignment. You save all the 3 bytes with the 6D in the middle, and because you don't have to catch the 0 bytes, you can use them. So this is what I did. So my knob-like instruction is at AL0, which actually does, as you see, plain nothing. And it is 0400. No realignment. Also, for byte modification, if I need to modify a single byte by a value that's in a range of like 10 or something, you can use increment byte PDR ds EAX, which is also FE00. And also what I didn't really understand was why Chris was using a add byte PDR instruction instead of, which is also available, move byte PDR, because, well, add byte PDR assumes that your middle bytes are 0. As we have seen on the translation pages, this is not always the case. So you should better use a move instruction instead of an add instruction. And placing the real shellcode, the second stage shellcode, at multiple at places that are multiples of 265 actually reduces the code size of the Venetian code dramatically. For a simple reason. It's a bit weird because it's a lot of like bit assembly, but if you look at this Unicode bullshit here, it's add EAX and then a number, because we get like every second 0 byte. That's the whole core problem, which means that you can easily add and subtract things from EAX that are in the second byte, but it's very hard to get stuff into EAX that changes the first byte here, because the only way to do that, unfortunately, is increment or decrement, which is a single byte command, and means that you have to pad the bytes again, so you have the 6D thingy in between, so it needs 4 bytes to increment it by 1. So if you place it somewhere where you can calculate without this byte, you save a lot of places, a lot of space. Yeah. So for the second stage shellcode, as I said, Dave used a shellcode that scans the stack and finds the real shellcode. Problem here is it's Unicode applications. So most of the stuff that's lying around on stack will be Unicode, which we tried really hard over the past 10 slides to get rid of. So that's not what you want. Your initial request, the pure Ascii stuff that you sent over in the first place, will be somewhere in memory. But where, you never know. It's most probably heap allocated stuff that you really don't know where. Now, do you really care about the CPU power your remote target has? And do you really care how long your shellcode needs execution on the target? Not really. It's not your computer after all. So, what I'm using for second stage code is make something useful out of this structured exception handler thingy. Because instead of like preventing Microsoft Word from displaying little boxes of crash messages, we can use that for shellcode by we start at 0, we start at the bottom of memory, we install a structured exception handler with the address here in this pseudocode of 5. So this is where the exception handler is. We loop scan for our code, like compare, is this my code? If not, loop, go to next byte, compare next byte, go on, on. If we find the code, of course, we execute it. But if we hit memory pages that do not exist or access violate, whatever, our SEH is triggered. So it jumps here, and our SEH just also increases the counter for the loop and goes back to step 3. So we can scan the whole 4 gigs mem for whatever place our shellcode ends up being. Fairly practical because you have multiple incarnations of your shellcode often, like different installations, whatever. You don't care. It has to be somewhere in memory, right? So this code is going to find it. And actually, it's not that much CPU power. On a gigahertz machine, it takes about 30 seconds to scan the whole memory and then find the code. This is the whole second stage code. I know it's probably hard to read. Can you guys in the back read it? Is it okay? Or should I just skip the slide? Yes, no? Okay, thank you. So you see, it's really simple. It's not that you need any libraries or any DLLs loaded or whatever magic Windows usually applies. It's really, really simple. You find out where you are. That's the, if you ever wrote something like this, you know what that is. And then you just install well, where's the SEH installation? Let me see, here. You just install the structured exception handler the way Microsoft says to do that. It's just those 5 instructions, and then you can loop, search, you have a search pattern, whatever. A 4-byte search pattern is descriptive enough so you can make sure that only your shellcode will have those 4 bytes. And, well, if you don't feel like relying on 4 bytes, take 8 bytes. It doesn't matter, it just increases the shellcode size by 2 instructions. Yeah, and then ink your counter, jump there. If you found it, just step over your little mark that denoted the beginning of your shellcode and jump to your shellcode. And as you see, the SEH does nothing else than installing it himself again, just to make sure that it's not going away, and increase the counter. And what I'm doing here is increase it not by 1, but by 1000, because, well, if you hit a memory page that is not mapped, you can be fairly sure that it will, the next page will begin at some even address. But you can change that. I mean, you can also increase by 1. That really doesn't matter. So, to create that all, you don't want to do that by hand, as I said. So, since I'm not believing in the Python hype, and I didn't really like make Unicode, I wrote a different generator for Venetian shellcode. This is like, yeah, I had to say that it's just 300 and something lines of code in Perl versus about several thousand in Python on, well, forget it. Good thing here being, doesn't matter in which language the generator is written, the resulting code is, funny enough, about 16 to 20% smaller than Dave's. That is just by the use of those magic instructions that are 2 bytes long and have the second byte being 0. Well, it also handles characters that you cannot transmit over the line, and has the already discussed second stage shellcode to scan the full memory. And will be on the webpage ready for download if I manage to do that, because this morning I forgot to upload it. So, putting it all to use. Now we spend so much time looking at the theory and blah blah behind it that, yeah, now let's have some fun. SAP Internet Transaction Server. It's a 3-tier architecture. It's widely used, actually. It has a front-end web server, standard web server, Netscape Enterprise, IIS, whatever, and has a special plugin on this web server. And this plugin takes the user request, cheers, and parses it and looks for things it's interested in. Like, you have HTTP requests containing all kinds of different header information. This plugin takes the request, parses it, and takes the elements that it's interested in, like the URL, user agent, the host tag, and some other stuff, puts it together and sends it to a middleware system. This middleware system, called A-Gate, is sitting behind that, taking the request, and actually doing all the SAP-like magic, translating it to the not documented protocols, and doing the not documented remote RPC calls, and doing all kinds of not documented things. And what basically talks to the R3 system in the backend. It's relatively, in terms of SAP, easy to install, runs on Windows or Linux, and it's directly connected to your R3 database. So it's also for your workflow, buzzword, and whatever, very practical, because you just basically place 2 Windows machines there and have an instant internet shop, which is what it is most commonly used for, that talks directly to your SAP, and so the order goes out automatically, and you can remotely fire people. This is stolen and copyright violated out of SAP's installation guide. This is where the security of the whole thing comes from. You have the front end, as they call it, HTTPS generic firewall, which is funny because the HTTPS generic firewall allows HTTP. Here you have your generic Microsoft web server, then a TCP/IP connection to the second host that is protected by, I don't know, a firewall. And then you have the connection to R3 that you can possibly place another firewall in between. Now, looking for vulnerabilities. As I said, format strings are almost extinct in open source, but in closed source, they're very easy to find, as we all know. So the front-end server has a format string vulnerability that is in the logging function. It's actually only if the logging is increased, that what often happens with format strings. You increase the log level, it calls more printf functions. Well, in this case, this is lethal. And then we have this A-gate that, as we have seen, sits directly behind a second firewall and is therefore highly protected. But because it copies all the data, the W-gate actually just copies all the data into a different format and sends it over, we have 4 remote buffer overflows. And I'm not saying it's just 4. So in your HTTP request, you have normal CGI parameters, in this case having command, runtime mode, or a session. You put lots of A's in there, you know what happens. Also, we even have a pure Ascii overflow because it copies for post requests with, what's that, MIME post, basically, like file uploads. There is this content type field, and there is this boundary tag for the MIME upload type, and that's copied as well directly in the request into A-gate buffer overflow, bam. Also, we have this nice little feature of hard-coded installation check routines. That means if you go to one of those systems and just type in a browser the request with command equals A-gate install check, you get a nice HTML colorful page with all installed DLLs, including the path, including the version, including the expected version. So we got a little bit info. Okay, break for administrative stuff. Being gray heads, of course, that's all checked with SAP. Now, here's the deal. The fixed information for those vulnerabilities we just discussed are in the SAP nodes component BCFESITS under those node numbers, but don't ask us what it means. Because SAP advisories and patches are only accessible if you supply a registration, which requires a customer, partner, or installation number. Being the poor hackers that we are, we don't have that. So, don't ask me if the stuff that you can download by today is O-Day or Stone Age Day. I don't know. It might be O-Day, but I don't know. So, I forgot the t-shirt, but I'm awarding a pH neutral t-shirt to whoever has an SAP account and can actually tell me what's O-Day and what not. But apparently, the ETS system in version 6.2, patch level 7, version 6.1, patch level 30, or version 4.0, patch level 460. I can't stand it. Apparently, those are fixed. So if you got one of those shops, use those versions. Okay, we're taking the techniques that we just discussed and put them into use. What we used actually for testing the different ways of doing stuff, for the runtime mode overflow that I'm bold enough to try to demo later, we used the SEH-based return, because that was the overflow that if you just overflow to the return address, you don't have anything useful in the registers. We use our Venetian shellcode and the discussed memory scanning. And, well, hacking is sometimes a question of quality, so the real shellcode is always high-verse. For the agate command overflow, we're actually using a direct return, because there we have a pointer to useful data directly in a register at return time. We actually use Dave Vitel's shellcode, which is practical because you can see the difference if you take the time at home and look at the debugger. And of course, the content type overflow is pure Ascii, so it doesn't really matter. But here again, the return address diffing functionality of the plugin comes in fairly handy for having good ODAs. The wget format string. I was thinking about possible ways to get the shellcode into this place and execute it. And I don't know if that's well known or not, but it's fairly easy to generate a format string out of shellcode that at execution time in the printf type of function instantly becomes your shellcode. Why? That's all the code you need for that. The only thing you need to know is how many characters were written before your format string gets executed, or interpreted in this case. And then you can, of course, always build the difference between one byte of your shellcode and the next byte of your shellcode, and just clutch them together in this type of string. And so this is your shellcode. And it's fairly practical because one printf call will actually translate it into your shellcode instantly, even at different addresses, which is one of the good features of format strings. And of course, your IDS will have no clue what's it. Another note regarding SAP. We had the pure coincidence that other people of the group in their professional lives could look at other SAP architectures that are hanging in the internet with a naked ass. So Nowin over there had a penetration test type of gig, and the mysap.com architecture is comparable to what I just explained for the ITS architecture, just that it contains even more strange types of servers. Now look at this. It is not copy and paste because I'm lazy, but it's copy and paste because it's real. You have a buffer overflow in handling of HTTP host tag in the message server. If you put more A's in the host tag, you have a buffer overflow in the web dispatcher. If you put more A's in the host tag, you have a buffer overflow in the application server. So, that is it, but no details yet because A, it's not fixed, and B, you remember the login thing and the advisories? We don't know. So, summing it all up, Unicode overflows are exploitable, pretty much like everything else. And yeah, that is just because it's Unicode, it doesn't protect you even more or less. Second point being, you can use your CPU power for something useful, like instead of finding little green people on Mars, why not finding little black root shells? And still, just because a platform, in parentheses, Cisco's printers, SAPs, are obscure and use strange little things and undocumented little protocols, it doesn't mean that not at some point will some sick, probably German guy come ahead and write an exploit for it. So, summary, you can download, hopefully when I fix this all, at least the plugin is already downloadable. Yeah, because we had this discussion before, at the end there's always sitting this little R3, and just to give you a taste of how software might react, this is a single UDP packet that you can send to our R3 system, and this single UDP packet will execute what... Other questions? Oh yeah, that is just a shell command. It's passed to create process as an argument. So
I had a discussion with one of those SAP security@sap.com guys as a follow-up to such kind of activities, and they basically told me that in regards of the web application server, it depends on the release hour, how stable it is.
Excuse me, did you just say it depends on the hour of the release, how stable? Okay. I think that totally speaks for itself. And go ahead, I'm still answering questions because I'm going to waste some time here trying to reboot the box and get stuff done.
Excuse me, do you have some magic tool for doing all your work?
A magic tool?
Magic tool, yeah.
Well, Ollie debug. No, yeah, that's pretty much it. Actually, I recommend if you didn't look at Ollie debug so far, look at it and, well, pay your tribute to the guy who writes it, because apparently he is a single crazy person that sits somewhere in Germany and writes a complete Windows debugger for free, which I think is fairly cool.
You said you don't care about how much CPU time it costs about scanning all the memory. So if you think about a production system which is probably equipped with some CPUs and some memory, what do you think is the real time it would consume to do that stuff?
I did some tests in regards to that. On a Pentium 2, the whole memory scanning takes almost a minute. On a gigahertz machine, it's between 10 and 20 seconds, something like that. So
It won't show up in the logs like 2 hours of scanning something.
No. It's in typical logging scenarios, like if you have a network management system that blinks red and says call your admin every time the CPU power runs too high, this won't actually trigger the threshold configured.
So if you then write an exploit code, what would be the typical kind of action you would do then? Is it something like on a web server you deface probably? What do you do with an SHP if you have control over it?
Well, first of all, that is one thing. I was thinking about that question, and I was actually expecting it. Thing being, this is the only way I know that you can remotely give yourself a raise, because if you take over like the middle tier application on a web shop, this web shop needs to have a fairly privileged SAP R3 account to do all the ordering and all the bullshit, right? So this one, of course, being plain text in some text file, config file, you own this machine, and of course, you have all the command line clients of SAP available, and you can basically do whatever you want in the SAP database.
Something like data mining.
Data mining or
Ordering stuff.
Ordering your, let's say, favorite police fellow, like 500 t-shirts, or I don't know. Okay, let's try to do a demo here. That's gonna fail badly, because every time I try demos, especially at CCC, they always fail, and I never know why. Okay, just a sec. The last demo actually failed with Cisco and Linux, so that doesn't count. Oh great, it doesn't ping. Yoo-hoo. What's the freaking problem? Looks okay to me. I hate demos. So, what's up here? What do? Oh, look, the little computer is blink. It works now, I think. Well, at least I get echo requests, and now get echo replies with it. So, let's take the magic red splash. So here we got this little, that's almost impossible to read, isn't it? Here we got this little A-gate process, be in the middle tier. Now let's see how badly my exploit fails after the connection itself didn't work. So it's running. Down here is the status thingy that tells you if it's running or dying. And now we're sending the exploit. No, we're not sending the exploit. What? Oh, it just took a while. Oh yeah, the exploit has the feature of using this A-gate installs check thingy to tell you exactly what DLL version it's using for the return address and what DLL version is installed, and lets you decide if that's worth the try or not. So let's try it. Oh, it crashed. Good, good. Now, we have a few little things here that are worth explaining, and I'm going to use the mouse to point things out. First of all, the return address, we're actually returning to two capital A's here, which should make any host-based IDS look strange at it. No, this is not a mistake. Remember, we're having the SEH address overridden, and the most reliable way to get an exception triggered is basically to return to two capital A's, because in code, if you look over here, it's the section that would usually be executed when you try to start this program under MS-DOS. And that tells you this program cannot be run in DOS mode. This section is always the same. And this section always has, for the capital A place, this following this interrupt 21 call, which is sure to trigger an exception here. So we got our exception. Now, let's jump into the exception handler of NTDL. Here we are. Now, this exception handler does some magic and calls an internal function, does some more magic, blah, blah, blah. Calls another internal function. Actually, at this point in time, it figured out we have an SEH and found the SEH and places pointers to the SEH on the stack. So we go in here. And this is what we were looking for. It found the SEH and it calls it. So this call ECX will execute our SEH. Now let's do that. So the SEH pointer we supplied points into, as you see at the top, into librfc32. One funny side note on SAP, one of the protocols they use is called RFC, remote function calls. And it's, despite the fact that it's called RFC, it's not documented. So I thought that's funny. So this place you have seen in the presentation before, this is where it does some pushing and popping and loading addresses, but we could address this place, and a few lines below that we have the call EBX. So step here, call EBX, yep. And now we're on the stack. Compare stack window down here has those addresses that are pretty near to those addresses. Here's a little bit of magic that I really like, because we return the pointer that we get in EBX points to the next SEH address. So it basically points 4 bytes before the return address we can supply. That's of course a problem because the return address will not be executable code. I mean, it's fairly hard to find a Unicode return address that calls a register. It would be almost impossible to find a Unicode return address that calls a register and becomes a useful instruction. So, of course, you have basically 4 bytes time to get rid of this. And the best way I found is with this little byte 81 in this context here, because that is a add divert PDR and then a number. So it will actually add this number, which turns out to be our return address, to some place. And since EAX points to writable memory, it just adds a number to a number. And so we got rid of the return address. Here, that is, if you check the disassembly here, this is exactly the address we return to. So, nothing happened. That's what we wanted. Now we adjust EAX. Here you see the padding bytes in action. And here you see the not bytes in action. Let's walk and walk. La 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 la. This actually happens because we align it to be on a second byte boundary. So we don't have to add too much to EAX all the time. Oops, there is the code. Now, let's see where EAX points to. You gotta love this debugger. Let's just fake a little bit here. Because if you do this, you will always highlight modifications in this window in red. You see down here, hopefully you see it, the intermixed 0 bytes and real bytes. So that's not going to be useful code. And this code over here is going to try to change that with a few instructions. So you see how it increments and changes bytes down there. Is that like, can you see that in the back? Yeah. So let's go on here. It's basically like opening one of the Überraschungseier and puzzling together your Lord of the Rings character. They don't ship Gollum in the Eier, don't they? And here you see the second stage shellcode in action. You have seen that on the slides, and here you see it goes ahead and just compares bytes, compares bytes, compares bytes. It's extremely boring. And now, boom, what happened? Access violation while reading 0001100. Well, no memory map there. Now, we're going to show the magic of unstructured exception handling in shellcode. I need both hands for the shift key. Back into the fellow exception handler. We've seen that code before. And here it calls the exception handler, which happens to be right in our shellcode, increasing the counter and jumping back into the place. And, well, got the next exception at the next place. So this is fairly boring and hard to show. So we're going to kill this little thing here. Good feature of SAP software for research, it always comes with a manager that restarts the process if it crashed or died. So I'm just going to fire up the exploit again and hope it's going to work. It's going to work. Hey. So, and now we need a task manager here. Yeah. So, this one is, Mumbi, how fast is this box? Do you know? Oh, yeah. We don't know how much CPU power that box has, but yeah, Windows doesn't know anything. Well, on this box here, I got a little prompt that says program files SAP ITS 2.0 programs. And if I type, who am I here, it says NT authority system. Let's see, take one of the other cool tools for Windows. Yeah. There's no R3 installed on the box. It couldn't handle a R3. So let's see here. Yeah, it's fairly telltale that this A-gate process actually has a child process called cmd.exe. Yeah, I guess that's it. Thanks for listening.